This video was sponsored by CuriosityStream, home to over 2,500 documentaries and nonfiction titles for curious minds. The Cantor set is weird. Infinite size, zero length, and a fractional dimension are all going to show up here. Plus, this is an introduction to some of the mathematics behind fractals, which 3 Blue 1 Brown has done a cool video on. And this is kind of like an intro to that. We're going to see similar ideas here, but unfortunately won't be as pretty. Anyways, what is the Cantor set? Well, it's just a bunch of numbers that lie between 0 and 1 inclusive. But which ones? To find that out and construct the set, what we do is take this set of real numbers, again between 0 and 1, including the endpoints, and this will be called C0. Then we're going to remove the middle 1/3 of this line segment, excluding the endpoints, as in we keep 1/3 and 2/3 in this next set, which will be called C1. Then keep going. Remove the middle 1/3 from each of these two line segments while leaving in the endpoints, so we produced 4 smaller line segments. This pattern would then go on forever. The Cantor set is simply the set of all numbers that are never removed, as we do this forever. That may take some time to digest, but now for certain numbers, it's a little more obvious whether they are or are not in the set. For example, 1/2 is not in the Cantor set. Yes, it's in C0, but then it gets removed, and the Cantor set is the numbers that are never removed. This means 0.46 is also not in the set. That's gone after C0 as well. 0.2 isn't there either. It survives the first cut, but it's gone after that. And same goes for 0.21. So now which numbers are in the set? Well, 0 is in there. We included the endpoints in C0, and 0 never gets removed since it's never in the middle third of any interval. Same goes for 1. That must be in the Cantor set as well. In fact, it shouldn't be too hard to see that all of the endpoints that are created in each new set must be in the final Cantor set. Look at 1/3. It becomes an endpoint in C1, and from there it will never be removed since it can't be in the middle of an interval anymore. 1/9 becomes an endpoint in C2, and that will never be removed, so it's in the Cantor set as well. 1/27 is in there, 2/3, and so on. You'll notice a pattern of only having denominators with an integer power of 3 in them. So now we know that the Cantor set is actually infinite. In the first set we have 2 endpoints. In the next set we have 4, then 8, 16, and we just keep multiplying by 2 forever. All those points won't be removed, meaning they're all in the Cantor set. So the Cantor set is infinite. It is not obvious at all whether there are non-endpoints in the final set though. But let's look at the second item on our list, because it seems like we're removing a lot of numbers as we go down these sets. But just how much? Well, the first set has a length of 1, of course. But that's not the length of the Cantor set, since the second set removes a length of 1/3. All those numbers can't be in the final set. Then the next set has a length of C1, or 1 minus 1/3, minus 2 of those 1/9 chunks. And the next set removes 4 of those 1/27 chunks, and this keeps going. Now realize this series here of just the negative numbers is geometric. Every term is being multiplied by 2/3 to get to the next. 1/3 times 2/3 is 2/9, times 2/3 again is 4/27, and using the infinite series formula, you'll find all the negatives sum to -1. Then we have 1 plus that -1, so the length of the Cantor set is 0. Just as a reminder, the set of real numbers from 0 to 1 is also just a bunch of points, infinitely many, just like the Cantor set. But this interval obviously has non-zero length, while the Cantor set does not. So are the infinitely many points in here more infinite somehow than the Cantor set? Well, let's see. Let's look at a point in the Cantor set such as 0. You should agree that after the first cut, our number, or any number, in the set will be either on the left or the right line segment. Can't be in the middle for sure, because that's gone. And 0 is obviously on the left side. But after the next cut, we find our number must be in the left portion of that first left cut, or on the right portion of that first cut. Or it's in the left of the right side, or the right of the right. Those are the only options, and 0 is in the left of the left. After another cut, we break all those options up into their own left-right section, and 0 is now in the left of the left of the left. If we keep going, we'd find the number 0 can be written as L, 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 L forever. It's like an instruction to find where the point will eventually be. Here, let's do the same thing with 1/3. 1/3 is on the left after that first cut, so its first letter is L. Then it's on the right of the next split, so the next letters R. Then the right of the next, and then the right of the next, and so on. So 1/3 can be written as L, R, 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 R forever. 2/9 would be L, R, then L's forever. 1 is all R's. And in fact, every number in the Cantor set can be written as an infinite list of L's and R's. If I went LR, LR, LR forever, well, that refers to the left third, then the right one after the split, then the next left one, and then right, and forever. It converges to some point. So, the Cantor set is every single combination of infinite L's and R's you could possibly have. Or we could replace L with 0 and R with 1. So the Cantor set is really every infinitely long binary number. But again, those binary numbers are nothing more than instructions telling us where that element is as we move down our sets. There's no way we could have a finite binary number in the set either, since a finite sequence of 1s and 0s, like 0, 0 or LL, would correspond to an interval that would lose its middle third in the next split. So we actually just discovered something pretty interesting about this set. The Cantor set is not just infinite, it's really infinite, or the actual term, it's uncountably infinite. It's a bigger infinity than some others, and here's what I mean by that. See, I can have a list of all positive integers. I can start at 1, go to 2, then 3, and continue this pattern, and I'll never miss one. Same goes for all integers, because I can start at 0, then go to 1, -1, 2, -2, and so on. These are infinite sets, but they're what we call countable sets, because they can be listed like this. They start somewhere, and following some rule or pattern will never miss a number. All infinite binary numbers, though, cannot be listed. That's an uncountable set. If you tried to make that list, even though it's infinite, you could give it to me and I could find an infinitely long binary number not on your list. Vsauce and Numberphile and plenty of other YouTubers have talked about this concept before, usually in regards to the set of real numbers, but the idea is the exact same with infinite binary numbers. My number would just start off by taking your first number and flipping the first digit. So this number will not be the same as your first one because they have different first digits. Then I'd take your second number and flip the second digit. And same goes for the third and its third digit, and fourth, and this pattern would continue. Thus, my number is different than all of yours. It can't match any of them because one of the digits is guaranteed to be flipped from yours. Thus, I have found an infinitely long binary number that is not on your list. So your list is not complete. This tells us the Cantor set is uncountable, which means it's a bigger infinity than the integers, for example. Those are countable. In fact, the Cantor set is just as big, or it has the same cardinality, as the set of real numbers. And that's weird. Actually, for me, that's probably the least intuitive part of this video. In the last video, we saw two infinite sets are the same size if you can map every element in one set to every element in the other without overlap and without missing anything. Hence, the positive integers and the positive even integers are surprisingly the same size. And the set of all real numbers between 0 and 1 is the same size as the set of all real numbers, since there exists a mapping that goes from each element between 0 and 1 to something different in the real numbers. And now we know the Cantor set is also just as big as all real numbers, meaning it's also just as big as all real numbers from 0 to 1, where this all started. So we remove infinitely many things in order to obtain the Cantor set, yet the size never changes along the way. Before, when I asked whether the top set was a bigger infinity since it has non-zero length, the answer was no. The Cantor set is just as big, and thus everything in it can be mapped to something different from 0 to 1 without missing anything. This hopefully kind of shows you how strange infinity is. The Cantor set seems like it should be smaller, since we keep removing more, but the size remains uncountable. And when you zoom into the Cantor set, you get a sense of that idea of infinity with this fractal-like behavior. Whew, okay, that was a lot of math. For those who need a break, here's some epic music followed by a possible ad. And we're back. So, the fractional dimension part. How does that come in? Well, let's just categorize integer dimensions first. We say a line segment is one-dimensional, a square is two-dimensional, and a cube is three-dimensional. But how are we defining dimension here? Well, here's one way. If I multiply the length of this line segment by 3, I get 3 line segments, obviously. Multiplying the length by 3 left me with 3 of the original thing. But if I multiply all the sides of a square by 3, I get a square that is 9 times bigger. Multiplying all lengths by 3 led to a bigger square that consists of 9 or 3 squared of the smaller squares. And for the cube, if I multiply all sides by 3, I get another cube that is 27 times bigger. Multiplying all lengths by 3 left me with 27 or 3 cubed original cubes. Notice that the exponent in each case matches the dimension of that object. So we can say this is what defines the dimension of something. When you multiply all sides by any positive number, not just 3, the entire shape gets bigger by a factor of that number to some power, and that power is the dimension. Now, I chose 3 because that's what we're going to use for the Cantor set. We're going to triple all those intervals starting with C0. So instead of going from 0 to 1, we're going from 0 to 3. Then after doing the middle third split, we get 2 intervals, one that goes from 0 to 1 and the other that goes from 2 to 3. But notice this is just what the real Cantor set starts with. Once we continue that same pattern, the left portion is just going to create the same Cantor set, while the right is going to create another Cantor set that is shifted, but it'll definitely be the same size. So for all those simple shapes, tripling the lengths led to something that was 3, 9, or 27 times bigger. But for the Cantor set, tripling all those intervals led to something that is 2 times bigger. We got 2 Cantor sets basically. But we have to write this number 2 as a power of 3, just like above. And 2 equals 3 to the power of natural log of 2 divided by natural log of 3, or roughly 0.631. That is the dimension of the Cantor set. This tells us that scaling all those intervals which are used to make the Cantor set doesn't change the overall size as simply as more familiar shapes. and the same thing can be seen with fractals as you scale those up and down. That's why this all relates to the mathematics of fractals. I'll link all these related videos down below, but if you want to explore some more real-world applications of patterns and chaos, then you can do so over at CuriosityStream, the sponsor of this video. This here is the same documentary mentioned in the last video, The Secret Life of Chaos, that covers patterns found in pure mathematics such as fractals, but also how patterns and chaos apply to computer algorithms, population growth, and just the universe around us. Another series they have related to all this though is Nature's Mathematics, which covers patterns and mathematical beauty found in nature, like is the case with the Fibonacci sequence. So there's a lot to explore on this platform for the math and science enthusiasts out there. CuriosityStream is available on a variety of platforms worldwide, and it only comes out to $2.99 per month. But if you sign up by using the link below, you'll get your first month's membership completely free, so no risk in giving it a try. And with this, you'll have unlimited access to top documentaries that I'm sure many of you will enjoy. And with that, I'm going to end that video there. Thanks as always to my supporters on Patreon. Social media links to follow me are down below, and I'll see you guys in the next video.